in section 1.3, which is about linear functions, is linear modeling. I want to give you an example. Let's consider an example that I mentioned before. Let's say your son.
Betty, I'm here now. Sorry I'm a little late.
It's okay. Let me fix the attendance. I think you're section 909.
Did you call my name, Esther?
Yes.
Okay.
Yeah, I saw your name. Yeah.
Okay.
Thank you for coming, Esther.
Thank you.
Let's consider this situation. Let's say your teenager son in the past 5 years, from 2020 to 2025. Just for the convenience of the numbers, I know 2025 just started. His height has grown 3 feet, right? In 2020, he was 3 feet high, 3 feet tall. And in 2025, he is 6 feet tall. So if we see a linear trending, if we see the rate of change, your son is growing, is a constant, then we can find a yearly, we can use a linear function to model this situation, right? If we let h, how about let's use y. If we let y be the height of your son, x is the time since 2020, then we can set up a linear function and use the linear function to model this situation. The linear function is going to be y equals mx plus b. This formula looks familiar, right? This formula is the slope-intercept formula. Slope-intercept formula for the equation of a straight line. We have variable x on the right side. We have variable y on the left side by itself. M here is the slope. Remember, for a linear function, for a straight line, the slope is the rate of change, is the average rate of change. For a linear function, the average rate of change is the slope. So we have, if your son's height has increased from 3 to 6 feet in the past 5 years, then over the 5 years, the total increase in his height is 3 feet, and use the total increase 3 feet to divide by 5 years, and we should have the yearly increase in your son's height, which is 0.6, right? So 0.6 is the average rate of change, which is the slope of the linear trend, and times x, and plus b here, we're going to use 3 feet. Why do we use 3 feet? Because x here is the time since 2020. That means we see 2020 as the initial year. We see 2020 as the initial year. We don't care what happened before 2020. If we see 2020 as the initial year, that means x equals 0 corresponds to the year of 2020. When x equals 1, the year is 2021. When x equals 2, the year is 2022, and so on and so on. As you can see, when we let x be 0, if we plug in x equals 0, y equals 3, right? Y here is the height. So when x equals 0, the year of 2020, your son's height is 3 feet. So everything matches. I want to stress the meaning of the slope and the y-intercept in a linear function. that model a situation, a real world situation. The slope here is always rate of change, the average rate of change. The slope here is the average rate of change. In this case, is the yearly increase in your sun's height. All right, the yearly or annual increase in your sun's height. So every year your sun's height grow 0.6 feet. Every year grow 0.6 feet. Every year grow 0.6 feet, right? And that's the slope in this linear model formula. And the y-intercept here, the value of b is the y value of the y-intercept, right? Is the initial value of the height, or the initial value of the dependent variable. Since it related to initial, we have to know what's the initial time. Depends on the situation, depends on the example. In our problem, here the example I give you, the initial year is 2020. You have to be careful with that. So the y-intercept, b, value of b, is the initial value of y. Okay, so I want you to remember when we use a linear function, y equals mx plus b to model a real-world situation. X here is the independent variable. A lot of times, X here is the time. Y here is the dependent variable. M here, the slope is rate of change. Rate of change is when X, let's say X is the time. When X go by a year or go by a day, really depends on the situation, the change in the dependent variable, the change in Y. So M here is the rate of change in the dependent variable every time X change 1 unit. And B here is the initial value of the Y. Okay, I hope this helped a little bit. And then when we look at this problem, I labeled the problem as 19. Probably is easier for us to understand. Let me erase this part. And I also can write it down what I said earlier. Y equals mx plus b. When we use this formula to model a real-world situation, which has a linear trend, M here is the rate of change. M here is the rate of change. It is the change in Y when X has changed by 1 unit. So the change in Y is caused by changing X, because X is the independent variable, Y is the dependent variable. Y depends on X. The value of Y depends on value of X. The change in Y is caused by the change in X, because X changes that lead to Y, the change in Y. So M here, the rate of change is how much change in Y when X make 1 unit change. B here is the initial value of Y, okay? So now let's look at a word problem or an application problem. In 1992, the moose population in a park was measured to be 3,870. By 1997, the population was measured again to be 5,120. If the population continues to change linearly, this is an important information. So this information tells us we are able to use a linear function to model the situation. So we are going to set up a linear model. We need to find a formula for the moose population P in terms of T. T here is the years since 1990. So now we know we're going to use this formula, right? The slope-intercept form, y equals mx plus b. X is the independent variable, y is the dependent variable. Specifically for our situation, for our problem, the y is p. We don't use a variable y anymore. We use a different variable, use p, because p is the initial population. So we're going to have p equals, let me write the slope-intercept form first, y equals mx plus b. So our y here is p, capital letter P, population. Our x here is t. T, the question says, pointed out, t here is the number of years since 1990. This is also very important. That means we see 1990 as the initial years. Right? So that means when t equals 0, the year we're talking about is 1990. When in the year of 1990, t equals 0, because t here is the years since 1990, right? So t equals 0 when the year is 1990. When the year is 1991, t equals 1. And so on and so on. When the year, so you can just keep going, right? The problem mentions 1992. So t is supposed to be equal to 2, right? Because 1992 is 2 years after 1990. And it also mentioned 1997. That should be 7 when t equals 7, right? And you can just keep going to find the value of t for a specific year since 1990. So that is t. We should understand that is t. Now let's find the value for m. M here is the slope. Remember, slope here is the average rate of change, right? It is the change in the population of the moose when the year goes by 1. When the year goes by 1. Here we use year as the unit of the time. Every year. So M here is going to be the yearly increase in the population of moose. How do we find that? Let's see, how do we find that? How do we find M here is a yearly increase in the moose population? M here is a yearly increase in the moose population. Isn't that very similar with the Is that very similar with the yearly increase in your son's height?
Yes.
Yes. So we have enough information to figure out the value of M. We have a 1992. In 1992, the moose population is 3,870, right? So when x1, when t1 equals, no, I'm not going to do. Yeah, when t1 equals 2. Well, you don't have to think about that. So from 19, let's just make it try to use common sense to solve the problem. From 1992 to 1997, that is 5 years. Over the 5 years, the population of the moose go up or go down? Or actually,
Increase.
it is increase. So increase, how much? So in 1992, it is 3,870. In 1997, is 5,120, right? So we can do this math. Do you agree? Is it? Let me double check this value. 50 and 12. 1,250, right? Do you agree, guys?
Yep.
Yeah.
Yep.
So yeah, let's just use common sense. Over the 5 years, from 1992 to 1997, over the 5 years, the most population has gone up 1,250, that many, right? Then we want a yearly increase. How do we find a yearly increase? Then we just use the total increase, 1,250 to divide by 5, right? Let's see, what do we have? 250, 250. So our M is 250. Do you guys agree?
Mm-hmm.
Yes.
Yeah. Over 5 years, the population gone up 1,250. So every year, the increase is 250. So we got our M, we got our slope. B, remember, is the initial value of the dependent variable. Here is the population of the moose. So B here is supposed to be the initial population. Initial year is 1990. So B here should be the population of the moose in 1990. Right? Yeah. How do we figure out the population in 1990 here? Is the information given?
Yes.
Where is it? In 1990.
That's where it's 0.
Yeah, T equals 0. But what about B? B here is the population of the moose. The population of the moose in 1990.
Could you just subtract 1,250 twice from the top? So it would be, would you just subtract the change?
Good idea,
Since it's
yeah.
2 years
So
times
yeah,
2?
exactly. So let's think about this. In 1992, the population is 3,870, right? Now what's the population supposed to be in 1991? Like a year earlier. If every year the population goes up by 250, then the year before 1992, which is 1991, should we have 50 less than 3,870? That should be, so let me write it down. In 1992, the population is 3,870. So in 1991, should be less, right? Because when the time goes by, the population goes up. So if we go backwards, the population should be decrease. So the year before that, we should have 250 less. So that is this number, minus 250, that is 620. Right? And what about 1991? 1990. So in 1990, we should have another 250 less, right? So we would have equals 3,370 minus 250, that is 5, yeah. Do you guys agree?
Yes.
Yep.
Yes.
So B value is 3,370. That's the most population in the year of 1990. Okay, we have our formula. The modeling formula P of T equals 250T plus 3,370. All right, so 1990 is 3,370. Then 1991, 250 more. 1992, another 250 more. So over the 2 years, we should have 500 more. 500 is a pretty convenient number. If we add 500 on top of 3,370, we should have 3,870. Okay, the number matches. Yeah, this is the correct answer. That's the model we have. All right. Why do we need a linear modeling? Linear modeling or any other type of mathematical modeling, one very important purpose or application is to predict. We use a model to predict the value of the function in the future, not a far away, but near future, probably. Like in the example that your son's height, you cannot expect your son grow 0.6 feet every year, right? Continually, never stop, that's not possible, right? At a certain point, it's gonna stop. But maybe you can use the model to predict 1 year, right? Possibly. Well, will not be too much off. And this situation is similar. Within a certain scope, we are able to use this linear model, this formula, to predict the population of the moose, which is the dependent variable y here in the future. Here in the future is 2002. Compare with 1990, it is a future, right? Okay, so how do we find the population in 2002? Maybe some of you want to continue try this way, right? 1997 population is 5,120. Then 1998, we have 250 more. Every year 250 more. Then just add 250 every year until 2002, right? One way to do that is that. But another way is to use the model we found in the first part. We can use the model we found in the first part, but in order to use the model to find the value of p, we have to know the value of t, right? In year of 2002, what's the corresponding value of t? In the year of 1990, the t value is 0.
12.
Oh yeah, exactly, 12. Perfect. This is important, okay? Please do not just plug in t equals 2002. No, t is not the year. T is the number of years since 1990. The meaning of the variable needs to be very clearly understood. So here t equals 12. In order to know the population in 2002, that is 12 years after 1990. And we just need to plug in t equals 12 to find the value for p, right? If we plug in here p of 12, we have 250 times 12 plus 3,370. We can do that quickly. Does that make sense? Every year 250. So over 12 years, the increase in the population is going to be 250 times 12. 250 times 12. And that is 3,000. So we add 3,000 on top of the initial population in 1990, and that is 6,370. And we complete the problem. I assure you, you will have something similar in the first exam, Unit 1 exam. And we only have time to cover one example. In Lumen, you can click the button, says similar problems. You can try different numbers. In a test, the similar problem will not be exactly the same number. So you have to be able to be flexible on that. When the number changes, you can still get it done correctly. We are learning the method. We are not learning a specific problem. We learn the method. If we know the method, then even the number changes, we still know how to solve it, right? Am I clear about this problem, linear model problem?
Yes.
Thank you. All right, so now we spend like 30 minutes on that. Now we're going to start section 1.4. Section 1.4 is about the domain and range of a function. The very beginning of the class, I started with the definition of a relation, right? Do you guys remember what is a relation? A relation is a set of ordered pairs, right? Anything that can be written as a set of ordered pair is a relation. Relation has a domain and range. Let's recall, what is the domain of a relation? The domain of the domain of a relation is a set containing all the first components in the pairs, right? The relation is is a collection of ordered pairs. Each pair has two components, first component and the second component. If we take all the first components and use the variable x to represent it, we use x to represent the first component, then all the first components make a set, that is the domain. Similarly, all the second components put together make a set, and we normally use the variable y to represent those values, and that is the range of the relation. We know function is a relation in the first place, right? So the domain range of a function is the same with the domain range for that relation, because the function is a relation. If we use the notational function, which is y equals f of x. This is a notational function, y equals f of x. There are multiple ways to represent a function. One important way to represent a function is an equation. And the equation connects two variables, variable x and variable y. So we write variable y on the left side of the equation by itself, and the right side should be an expression in terms of x. X here is the independent variable. Y here is the dependent variable. Y is wife, right? Wife depends on husband financially. So X is independent, Y is dependent. And all the possible values for X make the domain. All the possible values for Y make the range. So all the possible values for the independent variable make the domain. All the possible values for y make the range. We need to remember values for x make the domain. Values for y make the range. All right, so let's practice. Let's identify the domain and range for functions. And I labeled here, we're gonna look at the problem in Lumen number 1, 2, 3, 4, 5, the first 5 questions. Let me stop share my note and let's share the web page, the browser for Lumen. This is Starfish. And this is the browser. Do you see the Lumen?
Yes.
Awesome. The first question. This is the first question. Write your answer as an ordered list enclosed in curly brackets. Curly brackets means a pair of braces. A pair of braces is a notation for sets. The function f of x is defined as a set or ordered pairs. Using that set of data, identify the domain and range of f of x. So this is a function, right? The function is given as a set of ordered pairs, ordered number pairs. Domain would be what? Don't forget, use this pair of braces. The pair of braces is above the pair of bracket on your keyboard. And we are going to list all the first components, right? All the first components or all the x values. We have negative 25. We have negative 22. Do you agree, guys? Do you see what's going on so far?
Yeah, but do they have to be in order from smallest to greatest?
If it doesn't say it, it doesn't have to be.
Okay, thank you.
3, and then next one is 17 and 21. Did I miss anything? 1, 2, 3, 4, 5, 6. 6 ordered number pairs. So we should have 6 numbers in the domain because they are all different. Okay, that is the domain. What about the range, guys? Do not forget to put the set of braces. And in the range, we are going to have all the second component, right? Isn't this the same with the very beginning of the semester? How do we find the domain and range for a relation? Same thing.
Mm-hmm.
Second component, the first pair second component is 86. Second component of the second pair 11, and then 29, 72, 63, 18. Do we have any repeating elements? In this problem, we do not, right? All the numbers are different. In case you have a repeating element in the domain or the range, do not write it more than once. Only write it one time. Okay, so that is it. I'm going to submit this problem. I got it right. Next. And do not, and unless you feel very comfortable, if you don't feel very comfortable, do you see here? Get a similar question. You should try this. Practice enough to make yourself feel comfortable about handling this type of problem. Next problem. So this time the function is given as an equation, right? F of x again is y. Y equals, the right side is an expression in x. Negative 2x squared plus 5. What's the domain? Anybody identify what type of function this is? Anybody identify what type of function it is? If you look at the right side of
It's
the
quadratic.
exactly, it's a quadratic. Perfect. In fact, you know, linear function, quadratic function, they are all polynomial function. Do you see the right side is a polynomial function? Here, I want you to include a sentence in your notes. You should take notes. The domain for any polynomial functions is all real. Yeah, could you please include that in your notes? The domain.
Sorry, the domain is.
The domain of any polynomial functions is all real. Let me see if I can type it in the chat to everyone. Okay, so the domain. Do you see my do you see I'm typing here in Zoom? Do you see my typing? No?
No,
The
I
domain
don't.
of any polynomial function. The domain of any polynomial function is all real. Means from negative infinity to positive infinity. I just sent you a message. Yeah, this makes me miss the ultra collaboration ultra in the past. It has better feature that I can type and students can see what I typed even before I share the message. Okay, so yeah, it is a quadratic, including linear. Even the degree is 3 or 4 or even higher, as long as the function is a polynomial. Polynomial function is when you write a function as an equation with variable y on the left side by itself, and the right side has a polynomial. As long as the right side is a polynomial, that is a polynomial function. Any polynomial function has a domain, all real. Okay, how do we put all real? This problem requires us to write the domain in the interval notation. So we'd like to use this parentheses, right? And do a negative infinity. Infinity is right here, and a comma positive infinity. We don't really need a plus in front of positive, so we assume default that as positive. And that means all real, okay? Net infinity to past infinity, that is all real. All right, guys?
That,
Why?
I'm sorry, is that just because it can be any numbers?
Yeah, it
From
could be
starting
any real number. You're right. Yeah, you might wonder how come any polynomial function has domain all real? Because we do not have a limitation or restriction for the value that x can assume. We do not have such restriction for variable x. X could assume any real number, positive, negative, 0, past infinity, net infinity. So any real number, we have no restriction on the variable x. All right. So this problem just have one part. And that's it. Okay. And I just noticed there are question help here, video, 3 videos. You can also message me this option. Okay, let's move to the next one. Question number 3. The function is given as a graph. We know the graph is a function because the graph passes the vertical line test, right? And here we need to find the domain and range for this graph. This would be the same with the first class we had this semester when we need to find the domain and range for a relation, right? Try to use the trick that I gave you. If you don't remember, that's fine. I'm going to repeat it. How do we find the domain and the range for a graph? Let's look at the domain first. To find the domain of a graph, we look at the graph horizontally, okay? Horizontally. Think about, you can look at the graph from left to the right or from right to the left horizontally. Think about, does this graph have a boundary from the left? Has a boundary from the left on the x-axis? Does the graph or curve has a boundary from the left? Like it is continue forever to net infinity, or it stops somewhere? And also consider, yeah, it stops somewhere, right? Very obvious because here we have a dot. It stops at what? At 95 or 93. We're considering the domain. So stops at 93, right?
-3.
Yeah.
Or is that, yeah.
Exactly. I'm using my big arrowheads, my mouse. It stops here. There's no curve to the left of 93, as you can see, right? So that means this curve has a boundary from the left, and the boundary is x equals 93, as you can see. Does this curve has a boundary from the right? And what's the boundary? Does the curve continue to past infinity, or it stops somewhere?
It stops at 1.
Exactly. That's the right boundary. Okay, so this is how do we do it, okay? So the left boundary is -3. The right boundary is +1. So we write the left boundary first, and then write the right boundary after, use a comma to separate them. And then we consider, since we need to write the answer in the interval notation, we need to consider, are we using parentheses or brackets? Because here we have a dot, solid dot, we're gonna use a bracket, a left-handed bracket. Oh, left-handed bracket to indicate 93, that value 93 is in the domain. Because this point, the blue point, is on the graph. Because that point has x value 93, so 93 is in the domain. So to include 93, we use a bracket to indicate that. On the right side, though, we do not use a bracket. We use a left-handed parentheses. Why? Because this point is not on the curve. This point is not on the curve. It's a circle. It's a hole, right? So the x value of that point, which is 1, is not in the domain. Because if 1 was in the domain, then this point is supposed to be on a curve, but it is not. It is a circle. Am I clear, guys?
Yeah, I understand it.
Yeah, I'm feeling a little bit different because I never teach online lab in the morning. Feel a little bit weird in the morning, stay at home here. So I try to make it clear. All right, that's the domain. So when you look at the domain, when you find the domain, look at the graph horizontally. Find the left boundary and the right boundary. Now we're gonna find the range for the curve. All right, range. To find the range for the graph, we look at the graph vertically, up and down, from top to the bottom, from bottom up, and we try to find the boundary from above and the boundary from below. Some of the graph might not have the boundary from above or below, right? Maybe the curve going up, continue, then the boundary is past infinity. Maybe the graph go down, continue forever, then the lower boundary, the boundary from the below is negative infinity. But here, does this curve has a boundary from above, have a boundary from below? You look at, does this curve has a boundary from below?
Yes.
Yes, right, 95 is the boundary. Below 95, below y equals 95, there's nothing. Below y equals 95, there's nothing. The curve stops at 95 from the bottom. And that's the left endpoint. And what's the upper bound? What's the boundary from above for this curve?
4.
Yeah, y equals 4. Very good. 4. And use comma to separate the two numbers. And now we consider parentheses or bracket. Do we use a bracket for 95 or a parenthesis for 95? Depends
A
on
bracket.
Yes. The reason we use bracket because 95 is in the range. Same reason. The blue dot is on a curve. So the y value of the dot of the point is in the range. Since 95 is included in an interval, we use a bracket, left-handed bracket. For here, we're gonna use a parentheses. Reason, oh no, I'm sorry. Use a bracket as well. My gosh. So for here, we use a bracket as well. Can you help me to figure out why do we use a bracket instead of parentheses? Earlier we use parentheses because there's a hole here. But when it comes to the range, the boundary from above is 4. How come 4 here? I use a bracket. I use a bracket to frame 4, indicates 4 is in the range. Why 4 is in the range? Guys, why 4 is in the range? Because this dot, I wish I can put a dot there. Let me see if I can. I don't think I have an option. So I'm pointing that dot. That point has coordinates 0, 4. Do you agree that point is on the curve?
Yes.
Yes. So the y value, which is 4, is in the range. That's the reason we use a bracket. In last semester, a lot of students messed up this type of problem, especially parentheses, bracket. They just don't really get it thoroughly. I want to make it very clear. The trick always works, but for the details, like the parentheses and the bracket, you need to be able to see the point. If the point is on a curve, then the x-coordinate of the point is in the domain. The y-coordinate of the point is in the range. If the point is not on a curve, then the x coordinate is not in the domain, we use a parentheses, then y coordinate is not in the range. So do you see this point? This point? Okay. How about this? I want to share my OneNote. This one, my OneNote. Do you see the curve?
Yes.
I'm trying to explain this point. Direct point. Direct point is on the curve. It has coordinates 0, 4. Since direct point is on the curve, its x value 0 is in a domain, its y value 4 is in a range. Okay, so 4 is in a range. That's the reason the range is 95 to 4 closed. 4 is included, so it's a bracket. All right. So let's go back the lumen. Submit. Next question, number 4. Find the domain of the function f of x equals square root ax minus 7. Give me 1 second, bear with me. Okay. All right. So let's see this problem. How do we find the domain for this function? What type of function this is? What type of function this is? What is that notation means? What is this? This is the radical symbol. So let me take a little bit of time to talk about radical expression. Let me use X. This is a radical expression. Radical expression has 3 parts. Firstly, the radical symbol. This is radical symbol. Secondly, n here is a root number. N here is the root number. We also call n index. N at least is 2. When n is 2, we normally do not really write it out. So if you see a radical without root number, that is default as n equals 2. When n equals 2, it is a square root. When n equals 3, that is a cube root. And also could be 4 or 5 or 6, higher whole numbers. So n here is a root number. When you do not see n there, when you do not have a number in that spot, that means the radical is a square root. The root number is 2, is defaulted as 2. X here is a radicand. I would strongly recommend you remember this word, radicand. Radicand. I know your major is not mathematics, But when you learn a new language, isn't that important to memorize the terminology besides the grammar? Mathematics, algebra is a language. It is important, or it helps you to study if you know those terminologies. So X here, whatever that is under the radical, it could be more complicated, just more than one variable, could be more an expression, right? That part, whatever under the radical, that part is the radicand. I can make it more complicated. So I can maybe write star here, right? Star here, the whole thing under the radical symbol. Star here is called a radicand. Radicand. So that's the structure of a radical function, radical expression. If you have a function which is represented by an equation with variable y on the left side and the right side, you have a radical expression, then you are looking at a radical function. You're looking at a radical function. How do we find the radical domain for a radical function? Yeah, I like to elaborate a lot. So very important. The radicand has to be bigger than or equal to 0 if n is even. This is something you need to include in your note. For a radical expression or function, the radicand has to be bigger than or equal to 0 if the root number is an even number. If the root number is 2 or 4 or 6 or 8 and so on, then the radicand cannot be negative. It has to be bigger than or equal to 0. Make it simple. Look at our function. There's no root number here, right? That means it is a square root. Square root, root number is 2, even number. So the radicand, anybody can tell me what's the radicand? Anybody can tell me what's the radicand?
8x minus 7.
Yeah, the whole thing, right? The whole thing. Very good. The whole thing under the radical symbol. That is the radicand. So the radicand ax minus 7, because it's the radicand of a square root. Root number is even, cannot be negative. It has to be bigger than or equal to 0. Okay, because this is the first time we see something like this, I try to elaborate more. And I think those information help you to understand. So write the radicand for this square root and then make it bigger than or equal to 0, and then solve that inequality. We are going to solve the inequality. This part is from foundation 2, right? Solve an inequality. Plus 7 plus 7. We have 8x bigger than or equal to 7, right? And then divide by 8, cancel. So we have x bigger than or equal to 7 over 8. Only when the value of x is no less than 7 over 8. The radicand is non-negative. And that will make this radical expression or radical function well-defined. The radicand for a square root cannot be negative because we are talking about functions in real number set. In a later chapter, when we learn complex number, that would be a totally different story. But here we are talking about real numbers. So the radicand has to be bigger than or equal to 0. When you see something like that, that's what you do. Make sure the root number is even. If you do not see a root number, that means it is 2. 2 is even. So you write or copy the radicand and make the radicand bigger than or equal to 0. And you will see, you will have an inequality. And you solve that inequality, you will have the solution set of the inequality, right? And that solution set would be the domain of the function. And you need to write the domain in the interval notation. So we are going to write the solution set in the interval notation. This means any real numbers or all any real numbers, any real that is no less than 7 over 8. On the real number line, let's say this is 0, this is 7 over 8. Bigger than or equal to 2, 7 over 8. So the interval has left endpoint 7 over 8, right endpoint past infinity. We always use parentheses to frame the past infinity or net infinity. At 7 over 8, the left endpoint, are we going to have a parenthesis or bracket?
Bracket.
Yes. How to understand that question? We need to consider if 7 over 8 in the domain or not, right? 7 over 8 is in the domain. 7 over 8 would make the radicand be 0, but that is fine. Radicand could be 0 for a radical square root. So included, we use a bracket, and that's supposed to be the answer for this problem. Is that clear, guys? In summary, when you see a radical function, if you do not see a root number, that means the root number is 2. So you are looking at a square root function. For a square root function, the radicand cannot be negative. So you copy the radicand and make it bigger than or equal to 0. 0 is fine, but cannot be negative, positive or 0. And you solve the inequality. You get a solution set of the inequality. And you write the solution set in the interval notation. And that interval would be the domain. Any real number in this interval could be the value for the independent variable. That's fine. It will make this expression, the function, well-defined. Let me know, is that clear, please?
Yep.
Okay, very good. Let me stop share the note and start to share the Lumen. This one here. Bracket 8 over 7 is this. 8 over 7, not 7 over 8, right? Yeah, 8 over 7. 8 over 7. And a comma. And then past infinity. Close with a right-hand parentheses.
It was 7 over 8.
Yeah, 7 over 8, exactly. Sorry. 7 over 8. My bad. 7 over 8. Submit. Right? Okay. Let's see, do we have one more? So my plan is, yeah, those are 4 questions. We have one more, number 5. Number 5. Let's do one more here. And this function I'm gonna introduce in my note, all right? Because this is something that you really need to know. Even you are not given. My note here. All right. Number 6 here. The function is supposed to be number 5. Okay. The function we are going to find the domain for is f of x equals 1 over x. Okay. What type of function this is? Hyperbola. Oh, we haven't learned that yet. In the future chapter we will. So this is the simplest. This is the most basic hyperbola function. So it is 1 over x. You know, y equals 1 over x. Isn't that a very simple function that you want to know the curve of the function, the graph of the function? The graph of the function is like this, right? It has 2 branches. It has 2 branches. As you can see, I can write this function as y equals 1 over x. The points on the graph of the function have x value and y value always multiply to +1. If we multiply x, you can see x times y equals 1, right? The points on the curve, the two components of the points always multiply to 1. In other words, the x value and the y value always be reciprocal of each other. So we can list some values, make a table to find some values. So this is x, this is y, y is 1 over x. So when x equals -3, y is -1 over 3. When x equals -2, y is -1 over 2. When x equals -1, y is -1, right? When x equals 0, what is y? Do you agree it's infinity? Can 0 be the denominator?
It's undefined.
It's undefined. Yeah, undefined. This does not exist, okay? It's undefined. X cannot be 0. Because if x equals 0 or approaches to 0, y approaches to infinity. I can write this way. When x approaches, y approaches to infinity. When x equals +1, y equals 1. When x equals +2, 1/2. When x equals +3, 1/3. So when x is positive, y is positive. When x is negative, y is negative, right? So we have two branches. One is in quadrant 1, the other is quadrant 3. In quadrant 1, the branch looks like this. I want to use different color. It passes 1, 1. If you plot those points on a curve in a rectangular coordinate system, and you will see a curve like this. And in quadrant 3, there's a -1, -1. Another branch is like this. It has two asymptotes, but you don't have to worry about asymptotes at this point. But I want you to see that when x approaches to infinity, y approaches to 0. That's why the curve goes down very low, but never touch x-axis. Yeah, think about if x is a million, if x is a million, a trillion, or even a zillion, very, very large number, that makes a y value very, very tiny, right? On the other hand, when x is a very tiny, tiny number, that makes y a very large, large number. That's why here goes up. Right here goes up, right? And the other branch is similar. So what's the domain of this function? We all know by common sense, denominator cannot be 0, right? Denominator cannot be 0. So the denominator of this function is x. So x cannot be 0. As long as the x cannot be 0, as long as the value is not 0, it could be a value in the domain. So the domain is all real except 0. How do we use interval notation to represent all real except 0? Is net infinity to 0, open interval, union 0 to +infinity. And you want to remember that. Okay, the domain, if you use the trick that I taught from net infinity to 0 and from 0 to +infinity. If you look at the curve horizontally, it doesn't have a left bound, doesn't have a boundary from left, doesn't have boundary from the right. However, it has a asymptote in the middle at 0. So you have to exclude the 0 from the real number set. This is the way we exclude 0. Net infinity to 0 open, union 0 to past infinity. And let's go back, Lumen. Is the curve the same with what I draw? The graph is shown on the Cartesian plane. The domain is negative infinity, comma 0, union. Let me see where to find the union notation.
Click on interval and it'll be there.
Interval? Oh, okay. Yeah, exactly. And another parenthesis, 0 to past infinity. You need to get used to this type of notation. Basically, you exclude 0 from all real. You exclude 0 from all real, so that it looks like that. What about the range? The range is the same thing, guys. The range is the same thing. As you can see from the curve, it is symmetric, right? It is symmetric. And you just need a copy paste. Don't know if you let me try copy paste. Not really. Okay, I'll just do it again. This is a negative infinity. Oh, it has a negative here. To 0. Here's a 0 to past infinity. Right? Let me challenge you with one problem. Let me stop share the browser and share my note again. My note is right here. I want you to find domain for function f of x equals 1 over x minus 2. Give you a couple minutes.
It'll be negative infinity to 2 with the union, and then 2 to positive infinity.
Very good. Are you Is Kaida talking? Oh no, sorry.
Yeah, that
I
was
see.
Kaida.
Oh, perfect. Exactly. So the way to do that is this function has a denominator, right? So if a function doesn't have a radical, doesn't have a denominator, you don't have to worry about the restriction for the domain. So basically, how to find the domain? To find the domain for a function is actually to find the restriction for the function. This function has denominator, so we do have a restriction for the function. The restriction is the denominator cannot be 0. Okay, denominator cannot be 0. X minus 2 cannot be 0. Then x cannot be 2, right? Because if x equals to 2, then the denominator would be 0. That's not okay. We all know denominator never can be 0. So 2 has to be excluded from the real number set. So the domain is all real except 2. How do we do all real except 2? This is a real number line. Let's say this is 2, right? So you're going to exclude 2. Exclude 2. And then all other numbers, they are fine. So my definition for a interval, it's not on the book. My understanding about an interval is one single piece on the real number line. So I give the meaning of an interval using a graph. All right, one single piece, and the piece has no disconnection on it. So as you can see on this rule number 9, I have 2 pieces. Do you agree? It's like if you use your hand to pick up one piece, you will have this piece. This is one piece. This is one piece. And this is another piece. So the domain has 2 pieces. You have to put them together. So you're going to union the 2 pieces. The first piece, the left end point, since this arrow has net infinity, doesn't stop somewhere, continue to net infinity. The right end point is at 2, both open, because at 2 is a circle, right? And the other piece, this piece, starts from 2, end with past infinity. Infinity always use parentheses. The reason we use parentheses for this 2 is because 2 is excluded. All right, so yes, this is the domain. Perfect. Thank you, Kaida. What about other students? Are you all understand? Do you have any questions?
No.
Very good. What if I give you another function that you need to help me to find the domain with? What if I give you the function, let's say g of x equals 1 over 2x plus 1? How do you find the domain? Yeah, made the denominator a little bit more complicated. Yeah, for this function g, what's the domain?
Two x plus 1.
Yeah, what's the domain? 2x plus 1 is the denominator. Domain, you need to give me an interval in the interval notation. To find the domain is actually to consider the restriction on the function. The function has a denominator, so it does have a restriction. The restriction is the denominator cannot be 0. Which value would make the denominator be 0?
Is it -1 over 2?
Exactly, very good. -1 over 2. Only -1 over 2 make the denominator be 0. So that number cannot be in the domain. Anything else is fine. So the answer is supposed to be net infinity to net half, open, open, union, net half to past infinity, open, open. You see that, guys?
Yeah, I understand it.
Perfect.
Mm-hmm.
What about the range? Let's look at f of x equals 1 over x minus 2. What's the range of the function?
Is the range the same as the domain?
No. The range is all real except 0. The domain is, this is a domain. The range is net infinity to 0, union 0 to past infinity. Because this function range, remember, is the value of y. Y cannot be 0. Y cannot be 0. Because the numerator is 1. When the numerator is 1, there's nothing we can do to make the expression to be 0, right?
Right.
Yeah. Y could be 2. Y could be 2. If we let x be So if x equals 5 or 2, yeah. If x equals 5 or 2, then y is positive 2. So it's okay. Y could assume the value of 2, but y cannot be 0. It's not possible for y to be 0. There's no way we can make a quotient with numerators 1 to be 0. What about the function g? This is the domain. What's the range? Function g, 1 over 2x plus 1. Is then that same thing?
Yeah, negative infinity to 0, union
Yeah.
and 0 to positive.
Perfect. All real except 0, right? Yeah, they are different. The domain and range is different. They have different domain and range is different. For this problem, the reason the domain and range is the same because this function is symmetric. Is symmetric. All right, guys. We finished the domain and range. Next class we're going to. There's another topic in 1.4. It is a piecewise function. So we want to leave piecewise function on Tuesday. We're going to take time to talk about this type of function, kind of special. But today we finished the domain and range. I hope the practice helps. You won't, basically, you will not have a very fancy function. You either will have polynomial function. Remember, if you have a polynomial function, the domain is always all real. If you have a polynomial function, the domain is always all real. Or they will give you a radical function. How do you find the domain for a radical function? Make sure the root number is even. By the way, if it's not even, is 3, then domain is all real, okay? Yeah, only when the root number is even, for example, 2, the radicand has to be bigger than or equal to 0. Then you solve the inequality, the solution set is the domain. Or you will be given some function with x in the denominator. Then the restriction would be the denominator cannot be 0, right? Then you just need to exclude the value that would make the denominator be 0 from the real number set to find the domain. So you only will see some functions like that. I hope we cover all the cases. All right, guys, keep trying, practicing in Lumen. Feel free to email me if you have any questions.
I have a question real quick. I think it doesn't, since I'm here, I don't have to do the email. Anyways, I know the class today, I seem not to understand, but it's okay. I'm gonna go back to the video because I was lost at some point far at the beginning of the class. I'll go back to that. That's okay. It's concerning the exams. How many questions should we be expecting? And are the questions multi-choices? The answers, I mean.
I remember it's 20
Okay.
on the exams. And what type of questions? When you work on your Lumen,
Okay.
that type of questions is the question you'll see in the exam.
Okay.
They are from the same question bank.
So it's not multi choices. I mean, like A,
Some
B,
of
C,
them,
etc.
yeah, some of them are multiple choice question. How about let's go to Lumen. This is a Lumen. Are you practicing in Lumen?
Yes.
Yeah, this will be the problems you will see. You know, because they are from the same test bank. They're from the same question bank. They're from the same pool. Maybe the number would be different. Get a similar question, so the number will change, right? The graph will change. Maybe you see this problem on your homework, but you will see a different curve in your exam. Does that make sense?
Okay.
Yeah, is there like a study guide for the test that
I
follow our
will work
tips.
on it. I will work
Okay.
on it.
And then once we go through the questions, once they're all done, can we go back and practice them again?
Sure, yeah. I will work on the study guide for exam 1.
Okay.
I think the important thing for you to get a good score, the important thing for you is you repeat the problems in Lumen.
Okay.
Do not just
Is
do
there any way
one time.
to see the explanation for the problems? Because like in my math lab, it would have how to do it, and I didn't really see that.
I
in
didn't
this
try this, but you can try. Earlier, I see the problem has videos.
Okay.
And also you can bring the problem to the class. I'll explain in the class.
Okay.
I will not give you the study guide right now because I want you to practice all the problems, right? And multiple times. I think if a student does not do well in the exam because the student did not practice enough in the homework assignments. For one type of problem, if you only practice one time, is far less than enough. Understanding is one thing. You have to practice multiple times in order for the knowledge really sit with you, stay with you. Okay, guys? Yeah, if you have any questions, please email me. Do you see there here, message instructor? You can message me here. Or say, see you. Bye-bye.
Bye. Thank you.
Bye. Thank you.
You're welcome. Bye-bye.
Bye.
Bye.